Everything we've been dealing with so far in our journey through chemistry has revolved around stability of electrons and where electrons would rather be in stable shells. And like all things in life, if you explore the atom a little further, you'll realize that electrons are not the only stuff that's going on in an atom. That the nucleus itself has some interactions or has some instability that needs to be relieved in some way, and that's what we'll talk a little bit about in this video. So, and actually the mechanics of it are well out of the scope of a first year chemistry course, but it's good to at least know that it occurs. And one day when we study the strong nuclear force and quantum physics and all the like, then we could start talking about exactly why these protons and neutrons and their constituent quarks are interacting the way they do. But with that said, let's at least think about the different types of ways that a nucleus can essentially decay. So let's say I have a bunch of protons. I'll just draw a couple here. Some protons there, and I'll draw some neutrons, and I'll draw them in a neutralish color. Maybe, let me see, like a grayish would be good. So let me just draw some neutrons here. How many protons? 1, 2, 3, 4, 5, 6, 7, 8. I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9 neutrons. And so let's say this is the nucleus of our atom. And remember, and this was, in the very first video I made about the atom, the nucleus, if you actually were to draw an actual atom, and it's actually very hard to draw an atom because it has no well-defined boundaries. The electron really could be, at any given moment it could be anywhere. But if you were to just say, okay, where's 90% of the time the electron is going to be, and you say that's the radius or that's the diameter of our atom, we learned in that very first video that the nucleus is almost an infinitesimal portion of the volume of this sphere where the electron will be 90% of the time. And the neat takeaway there was that, well, most of whatever we look at in life is just open free space. All of this is just open space. But I just want to repeat that because that little infinitesimal spot that we talked about before, where even though it's a very small part of the fraction of the volume of an atom, it's actually almost all of its mass. That's what I'm zooming out to this point here. These aren't atoms, these aren't electrons. This is we're zoomed into the nucleus. And so it turns out that sometimes the nucleus is a little bit unstable, and it wants to get to a more stable configuration. We're not going to go into the mechanics of exactly what defines an unstable nucleus and all of that. But in order to get into a more unstable nucleus, sometimes it emits what's called an alpha particle, or this is called alpha decay. Alpha decay. And it emits an alpha particle, which sounds very fancy. And it's just a collection of neutrons and protons. So an alpha particle is 2 neutrons and 2 protons. So maybe these guys, they just didn't feel like they fit in just right. So they're a collection right here. And they get emitted. They leave the nucleus. So let's just think what happens to an atom when something like that happens. So let's just say I have some random element. I'll just call it element E. Let's say it has p protons. Actually, let me do it in the color of my protons. It has p protons, and then it has its atomic mass number is the number of protons plus the number of neutrons. I did the neutrons in gray. Right? So when it experiences alpha decay, what happens to the element? Well, its protons are going to decrease by 2. So its protons are going to be p minus 2. And then its neutrons are also going to decrease by 2. So its mass number is going to decrease by 4. So up here you'll have p minus 2 plus our neutrons minus 2. So we're going to have minus 4. So your mass is going to decrease by 4, and you're actually going to turn into a new element. Remember, your elements were defined by the number of protons. So in this alpha decay, when you lose those, you're losing 2 neutrons and 2 protons, but especially the protons are going to make you into a different element. So if we call this element 1, I'm just call it, we're going to be at a different element now, element 2. And if you think about what's generated, so we're emitting something that has 2 protons, and it has 2 neutrons. So its mass is going to be the mass of the 2 protons and 2 neutrons. So what are we emitting? We're emitting something that has a mass of 4. So if you look at what is 2 protons and 2 neutrons, actually I don't have the periodic table on my, I forgot to cut and paste it before this video, but it doesn't take you long on the periodic table to find an element that has 2 protons, and that's helium, and actually has an atomic mass of 4. So this is actually a helium nucleus that gets emitted with alpha decay. This is actually a helium nucleus. A helium nucleus. And because it's a helium nucleus and it has no electrons to bounce off its 2 protons, you would call this would be a helium ion. So it would essentially, it has no electrons, it has 2 protons, so it has a +2 charge. +2 charge. So an alpha particle is really just a helium ion, a +2 charged helium ion that is spontaneously emitted by a nucleus just to get to a more stable state. Now that's one type of decay. Let's explore the other ones. So let me draw another nucleus here. I'll draw some neutrons. I'll just draw some protons. So it turns out sometimes that a neutron doesn't feel comfortable with itself. It wishes that it looks at what the protons do on a daily basis and says, you know what? For some reason, when I look into my heart, I feel like I really should be a proton. If I were a proton, the entire nucleus would be a little bit more stable. And so what it does is, to become a proton, remember, a neutron has neutral charge. So what it does is it emits an electron. And I know you're saying, Sal, that's crazy. I didn't even know neutrons had electrons in them and all of that. And I agree with you. It is crazy. And one day we'll study all of what exists inside of the nucleus. But let's just say that it can emit an electron. And when it emits an electron, so this emits an electron. So it emits an electron. And we signify that with its mass is 0. We know an electron really doesn't have a 0 mass, but we're talking about atomic mass units. If the proton is 1, an electron is 1/1836th of that. So we just round and we say it has a mass of 0. Its mass really isn't 0. Its mass, and its charge is -1. Its atomic, you can kind of say its atomic number is -1. So it emits an electron, and by emitting an electron, instead of being neutral, now it turns into a proton. It turns into a proton. And so this is called beta decay. Beta decay. Beta decay. And a beta particle is really just that emitted electron. So let's go back to our little case of an element. It has some number of protons, and then it has some number of neutrons. So you add the protons and the neutrons, and you get your mass number. When it experiences beta decay, what happens? Well, are the protons changed? Sure, we have one more proton than we had before because a neutron changed into one. So now our protons are +1. Has our mass number changed? Well, let's see. The neutrons goes down by 1, but your protons go up by 1. So your mass number will not change. So it's still going to be P plus N. So your mass stays the same, unlike the situation with alpha decay. But your element changes. Your number of protons changes. So now once again you're dealing with a new element in beta decay. Now, let's say we had the other situation. Let's say we have a situation where one of these protons looks at the neutrons and says, you know what? I see how they live, and it's very appealing to me. I think I would fit in better, and our community of particles we could call them of particles within the nucleus would be happier. If I too were a neutron, we'd all be in a more stable condition. So what they do is that little uncomfortable proton has some probability of emitting, and now this is a new idea to you, a positron, not a proton. It emits a positron. And what's a positron? It's something that has the exact same mass as an electron. So it's 1/1836th of the mass of a proton, but we just write a 0 there because in atomic mass units it's pretty close to 0. But it has a positive charge. And it's a little confusing because they'll still write E there. Whenever I see an E, I say, oh, I think an electron. But no, they say E because it's kind of like the same type of particle, but instead of having a negative charge, it has a positive charge. This is a positron. Positron. And now we're starting to get kind of exotic with the types of particles and stuff we're dealing with. But this does happen. And if you have a proton that emits this particle that pretty much had all of its positive charge going with it, this proton turns into a neutron. And that is called positron emission. Positron emission is usually pretty easy to figure out what it is because they call it positron emission. So if we start with the same E, it has a certain number of protons, a certain number of neutrons. What's the new element going to be? Well, it's going to lose a proton, p minus 1, and that's going to be turned into a neutron. So p is going to go down by 1, n is going to go up by 1, so that the mass of the whole atom isn't going to change. So it's going to be p plus n, but we're still going to have a different element, right? When we had beta decay, we increased the number of protons, so we went kind of to the right in the periodic table, or we increased our, well, you get the idea. When we do positron emission, we decreased our number of protons. And actually, I should write that here in both of these reactions. So this is the positron emission, and I'm left over with one positron. And in our beta decay, I'm left over with one electron. They're written the exact same way. You know this electron because it's a minus 1 charge. You know this is a positron because it has a plus 1 charge. Now, there's one last type of decay that you should know about, but it doesn't change the number of protons or neutrons in a nucleus, but it just releases a ton of energy, or sometimes a high energy photon, and that's called gamma decay. And gamma decay means that these guys just reconfigure themselves, maybe they get a little bit closer, and by doing that they release energy in the form of a very high wavelength electromagnetic wave, which is essentially a gamma. You could either call it a gamma particle or a gamma ray. And there's very high energy. Gamma rays are something you don't want to be around. They're very likely to maybe kill you. So everything we did, I've said a little theoretical. Let's do some actual problems and figure out what type of decay we're dealing with. So here I have 7 beryllium, where 7 is its atomic mass. And I have it being converted to 7 lithium. So what's going on here? My beryllium, my nuclear mass is staying the same, but I'm going from 4 protons. I'm going from 4 protons to 3 protons. So I'm reducing my number of protons. My overall mass hasn't changed, so it's definitely not alpha decay. Alpha decay was, you're releasing a whole helium from the nucleus. So what am I releasing? I'm kind of releasing one positive charge, or I'm releasing a positron. And actually, it's here in this equation. This is a positron. Positron. So this type of decay of 7 beryllium to 7 lithium is positron emission. Fair enough. Now let's look at the next one. We have uranium-238 decaying to thorium-234. And we see that the atomic mass is decreasing by 4, minus 4. And you see that your atomic number is decreasing, or your protons are decreasing by 2. So you must be releasing essentially something that has an atomic mass of 4 and an atomic number of 2, or a helium. So this is alpha decay. So this right here is an alpha particle. Alpha particle, and this is an example of alpha decay. Now, you're probably saying, hey, Sal, wait, something weird is happening here, because if I just go from 92 protons to 90 protons, I still have my 92 electrons out here. So wouldn't I now have a minus 2 charge? And even better, this helium I'm releasing, this helium, it doesn't have any electrons with it. It's just a helium nucleus. So doesn't that have a plus 2 charge? And if you said that, you would be absolutely correct. But the reality is that right when this decay happens, this thorium, it has no reason to hold on to those 2 electrons. So those 2 electrons disappear and thorium becomes neutral again. And this helium, likewise, it is very quick. It really wants 2 electrons to get stable, so it's very quick to grab 2 electrons out of the wherever it's bumping into, and so that becomes stable. So you could write it either way. Now let's do another one. So here I have iodine release. Let's see what's happening. My mass is not changing. So I must just have protons turning into neutrons or neutrons turning into protons. And I see here that I have 53 protons, and now I have 54 protons. So a neutron must have turned into a proton. A neutron must have gone to a proton. And the way that a neutron goes to a proton is by releasing an electron. And we see that in this reaction right here. An electron has been released. And so this is beta decay. This is a beta particle. Beta. This is beta decay. And that same logic holds. You're like, hey, wait, I just went from 53 to 54 protons. Don't I have, now that I have this extra proton, won't I have a positive charge here? Well, you would. But very quickly, this might get, maybe it probably won't get this exact electrons. There's so many electrons running around. But it'll grab some electrons from some place to get stable, and then it'll be stable again. But you're completely right in thinking, hey, wouldn't it be an ion for some small amount of time? Now let's do one more. So we have 222 radon. It has an atomic number of 86, going to 218 polonium with atomic number of 84. And this is actually just an interesting aside. Polonium is named after Poland because Marie Curie, she at the time, Poland, this was at the turn of the last century, around the end of 1800s, Poland didn't exist as a separate country. It was split between Prussia, Russia, and Austria, and they really wanted to let people know that, hey, we think we're one people. So they discovered that when radon decayed, it formed this element. They named it after their motherland, after Poland. So just it's the privileges of discovering new elements. But anyway, back to the problem. So what happened? Our atomic mass went down by 4. Our atomic number went down by 2. Once again, we must have released a helium particle, a helium nucleus, something that has an atomic mass of 4 and a atomic number of 2. And so there we are. So this is alpha decay. Alpha decay. We could write this as a helium nucleus, so it has no electrons, and we could even say immediately that this would have a negative charge, but then it loses